Okay, we're making this video in class about U-substitution. Okay, so what we're going to have is we're going to have some integral of maybe, I don't know, 3x times the square root of x squared plus 9, right? Something a little bit on the ridiculous side. A product of two functions, or maybe a composition of two functions, or something. Right? So we haven't really talked about how to take the integral of a product. But what we're going to do here with u substitution is we're going to call this function u. Okay? Whatever the crazier part or the more complicated part is, we're going to call u. And then we're going to find a way to replace these guys. Right? We don't want to have any x's in our problem anymore. We're just going to have u. Because if we're taking the derivative of u du, right, or rather the antiderivative, then hopefully this is an easier antiderivative, or an easier function to antiderive. Okay, that the antiderivative of this is something much easier than the antiderivative of that would be. Okay, so that's basically the point that we're going to do here with u substitution. Is we're trying to make our integral easier to algebra, right? Because algebra is the hard part of calculus. So we're going to try and make the algebra as easy as we possibly can. Okay, so let me take a picture of our worksheet for today. It will magically appear right now. So here are some problems from our class that we're working on. Okay, so we're going to start in the top left corner, and we are going to find something to call u. Okay, well, first of all, let's make this a little bit easier by applying one of our integral properties. Okay, so notice this is 3 times the cosine of 3 function. Yes, do you notice that? Mm-hmm. Well, let's take this multiplier and put it on the outside. So 3 times the integral of cosine 3x dx. Okay? So let's do that first. We're going to do that with a lot of our multipliers. If there's a constant times something on the inside, it will often behoove us to pull that outside. Okay, sometimes it's good to leave it in, but sometimes it's good to take it out. Okay, so let's see. What is the function that we're going to call u? Right? If we're going to find something using u substitution, we have to replace. Now, we want to keep the cosine, right, because that's something that we know how to take the antiderivative of, hopefully. Right? So cosine by itself is pretty simple. So let's just call this part u. So we're going to let u be the 3x part of our cosine function. Okay? So then what we do is we also take the derivative of this function we're calling u. So what's the derivative of 3x? Just 3. But we multiply it by dx. Okay, just like we did when we had implicit differentiation, there is not a u on this side, right? So we're taking the derivative of 3x, but then we also have this derivative of x business, sort of like implicit differentiation. Just always remember that when you're taking the derivative of your u, you always have to have that dx part. Okay, because we don't want to have any x's in our new function, right? So we have the cosine of u, and it would be really nice if this wasn't dx, right? We want to take the antiderivative with respect to u. So what we're going to do over here is we're going to solve this for dx. Okay, so once we find u and we take the derivative of it, we solve it for dx, so that once again we can do some substitution. Okay, this is the substitution part of our u substitution. So not only do we replace 3x with u, we also replace the dx part. Okay, also replace the dx part. Okay, so I guess looking at this, we could have, maybe we could have left the 3 on the inside. Right, because if I do some multiplication, I have 3 cosines of u times du over 3. So it looks like the 3's will cancel out for my problem to begin with. Right? Sometimes that happens wonderfully well, and sometimes it doesn't. Okay, so it might just look at the way the problem is setting up and see if you want it on the outside or the inside. It will cancel out eventually anyway. Okay, that's the beautiful part. So we are trying to integrate basically cosine of u du. Okay, which may or may not be a lot simpler than this one up here. Okay, so looking at this, what is the antiderivative of cosine? That is just sine of u, right? Plus some c value. Plus some c, right? That c comes from our initial condition. So anytime we're going to take the indefinite integral, right? We don't have any numbers here, which is why it's an indefinite integral. You're going to have a plus c after your antiderivative. Okay? So now that we have sine of u, what was our u value to begin with? 3x. So then the last thing we do is you plug your u back in, and I'm running out of space. Sine of 3x plus c would be the answer to the integral of 3 cosine 3x dx. Okay, let's go to the right and see what we have here. Oh, gee. Okay, we have the third root of x squared plus 5 dx. So let's make this x squared plus 5 be your u value, okay? That's part of our more complicated part. It's the stuff underneath the radical. So we're going to call u x squared plus 5. Okay, remember, we want something to cancel out hopefully at the end. So what is the derivative of x squared plus 5? Right? 2x dx is the derivative of x squared plus 5 with respect to u. Okay? So we write down what your u value is. What is our substituting? How are we defining u? We take the derivative of that and dx, and now we have to solve this for dx so we can replace it here also. Okay? So what do we get when we solve this for dx? Dx equals du over 2x. Okay? So now let's get to doing some substituting and replacing. So I still have a 2x. I have the cube root of. This whole entire stuff gets replaced with u. And I'm replacing dx with du over 2x. And remember, this is all multiplication. So guess what can divide itself out? The 2x and the 2x. Okay, and the way that calculus kind of designs these problems is so that cancellation or that division can happen. Okay, so the way that these are designed, that is supposed to happen. So we're basically taking the antiderivative of the third root of u du. Okay, which was much simpler than what we had to begin with. Okay, and that's the whole point of doing this u-substitution stuff, is to make your antiderivative simpler. Okay, so let's rewrite our root as a polynomial. So this is u to the 1/3 power. So then now we can use our polynomial rule of antiderivatives. So this is u to the 4/3, because we add 1, right? The rule says add 1 to the power and then divide by that power. So u to the 4/3 divided by 4/3 plus c. Okay, don't forget about the plus c that you would find if we had some sort of initial condition. Okay, so then rather than dividing by a fraction, we're going to multiply by the reciprocal. So 3/4 of u to the 4/3 power plus c. And now let's go back, since we're done with all of our simplifying, we're going to replace u with our original function. Okay, so I'm going to come vertically. I know that's not very kosher, but let's come vertically. And we'll replace u with x squared plus 5. Plus c. So don't forget about the plus c part. I almost did. Plus c to complete our antiderivative. Okay, so there is some U-substitution, right? It's supposed to make our algebra simpler. It's supposed to make our your integral easier to anti-differentiate. Okay, now that's your opinion whether you think it's simpler or not. But this is the way that we do it. Okay? What else can we do? How about we do sine one, another trig. Okay, so let's try this one right here. What are we going to call U? This stuff inside of our parentheses. We're going to call U 2x plus 3. Right? That's the complicated part. Sine by itself is not complicated. It's just a trig function. So we're going to call the complicated stuff 2x plus 3. So what is the derivative of 2x plus 3? 2, and don't forget to times it by dx. So 2 dx. Anytime you take a du, there's going to be a dx at the end. Okay, so we're going to solve this for dx because we want to substitute, and we can't substitute without solving. So we're going to replace dx with du divided by 2, and we're going to replace that one with just u. Okay, so we have the integral of 2 sine of u du divided by 2. Okay, so we see nicely that this 2 under our du and the 2 in front of the sine cancel out. So we're basically just trying to take the antiderivative of sine of u du. Okay, much simpler than the sine of 2x plus 3. Okay, that's my opinion. You might not think so. So what is the antiderivative of sine? Negative cosine of u plus c. The antiderivative of sine is negative cosine. So if we go back and do our one last step and resubstitute in for u, right, replace our u back with your x stuff, that's the negative cosine of 2x plus 3 plus c. Okay, let's try the next one together. So, what's the more complicated part that you want to call u? All the stuff on the bottom. Okay, that's the more complicated part. It has a power, so we're going to call u x squared plus 2x. Okay, and remember what's supposed to happen is some things are supposed to cancel, right? So that's the beauty of these, is that we're looking for some canceling. So let's take the derivative of our x squared plus 2x, which is 2x plus 2 times du. I mean, sorry, not du, but dx. So let's erase, sorry. This is supposed to be dx over here. So then we solve for dx, and we get du divided by 2x plus 2. Okay, so that's what's going to replace dx. We're going to replace dx with du plus 2, and we're going to replace our denominator with u. So we have 2x plus 2 over, okay, here's your u value that we decided to call u, so we're substituting u on the bottom. And then dx is du over 2x plus 2. Okay, so look at what magically simplifies, right? And this is the way that these things are supposed to happen. So let's do our simplifying. We can cancel out this and this, right? That happens nicely. So we have the integral of 1 over u du. 1 over u du. Okay, so hopefully you have done enough of these, which I doubt, but hopefully you have, to recognize the antiderivative of 1 over x, or in this case 1 over u, which is the natural log of u. Okay, so a 1 over a variable is the derivative of a natural log. So this is an antiderivative for your natural log. Plus c. Right, so 1 over u has an antiderivative of natural log. So now we're going to replace our u value, right, with what we called u up here. Right, so the last thing we do is we do some more substitution. We resubstitute, and that's going to be the natural log of x squared plus 2x plus c. And if we had an initial condition, we could solve for c and figure out exactly what that y-intercept is going to be for our function. Okay, hopefully these are becoming, I think we can skip this one. That's, actually, let's do this one, JFF, just for fun. Okay, so once again, this is your u. Okay, 3x plus 2. du is 3 times dx. So dx is du over 3. Okay, so we're doing our substitutions. This is the cosine of u times du over 3. Okay, so notice here, things don't cancel out, do they? They do not cancel out. So here is where we're going to replace all, well, let's just watch here. Right, we have something divided by 3. I'm going to bring that to the very front and call it 1/3 times the cosine of u times du. Okay, and this is perfectly mathematically legal since it's basically multiplication. All right, so we're dividing du by 3. That's the same thing as if we divide the whole entire function by 3. Right, because it's basically multiplication. There's no pluses, there's no minuses, so it's okay to do that. In fact, it's okay to take this 1/3 and put it outside of your integrand. That is perfectly okay also, one of the properties of integrals. So if things don't cancel out and it's numerical, then you take that scalar multiplier and you put it in front of your integral. You don't even worry about using it in the antiderivative because it would stay there anyway. It would be a part of your answer. It doesn't go away like it does with a derivative when you take an antiderivative. So now we have 1/3. The antiderivative of cosine is once again sine. And let's just go ahead and replace our u value right now. 3x plus 2. And then we have to add our plus c. Okay, so the 1/3 in front happens because when we would derive this, we would take the cosine of this and then multiply it by 3, and that would eventually cancel out. Okay, so if it doesn't divide out perfectly like it has in our first 4 examples, okay, that just means that it's going to be a scalar multiplier in the front. So let's see what happens with this guy, or gal if that's the way that you want to call it. So we're still going to call your underneath your radical the u part. Okay, make the more complicated part of our algebra the u, so that we can do a little bit of simple derivatives. So if u is x squared plus 2, then du is 2x times dx. Okay, so then if we solve this for dx once again, we get du over 2x. Okay, and we always want to have a dx so we can replace and only have u's in your antiderivative. Okay, so we're always going to have a u in your antiderivative. We don't want to have any x's. So u is underneath your, I guess I made my radical kind of long, didn't I? I can shorten that up. du over 2x. Okay, so in this case, I can't cancel out everything. Only the x here cancels with the x there. Okay, so we have a 3/2 as now our scalar multiplier. Right, we're multiplying the square root of u by 3/2. And you'll get to do this, it'll be pretty come second nature that whenever we have a scalar multiplier, you're going to move it to the outside of your integral. Okay, so that's going to be a pretty common practice that I'm going to do without talking about it very often. Okay, so we're going to take your scalar multiplier and move it to the outside of your integral. Okay, so this is once again 3/2 times the integral of u to the 1/2. So we're going to anti-differentiate u to the 1/2, which was u to the 3/2 divided by 3/2. Sorry, divided by 3/2. Right, when we add 1 to 1/2, 1/2 plus 1 is 3/2. So multiplying by the reciprocal cancels out that leading coefficient. That is very handy. So let's do our substitution. We called u x squared plus 2. So this is x squared plus 2 raised to the 3/2 power plus c. So parentheses x squared plus 2 raised to the 3/2 power plus c. So your whole entire thing won't always cancel out, but sometimes it does. And if it's a number, then you bring the number to the front. All right, I know the video is going a little bit long, but let's take a look at our e to the 3x. Okay, so what do you want to call your u value? 3x. So we're going to call the variable our u value. We're going to make u equal to 3x. That means du is 3 times dx, right? The derivative of 3x is just 3, right? That's the slope there, times dx. So then du divided by 3 equals dx. So let's do our substitution. The integral of 5e e to the u times du over 3. Okay, so here's your numerator, here's your denominator. We're going to pull that whole entire fraction outside of your integral. So we just have the integral of e to the u du. And what is the antiderivative of e to itself? Well, that's just e to itself. So the antiderivative of e is e plus c. Okay, so now we're going to come back in. Hopefully you have an eraser. We're going to put our 3x back in your numerator. And this is going to be your antiderivative, your integral of 5e to the 3x dx. Okay, so you pick a u value, you take the derivative times dx, you solve for dx, and then you substitute and anti-derive. Okay, hopefully it's a little bit easier to do it that way. Okay, so I'm going to do this one real fast. In fact, I'm going to pause the video and then the answer will magically appear. So we are calling the 2x squared plus 3 your du. Okay, so we solve for dx when we take a derivative. We replace and cancel, so the x's cancel and the 3/4 comes to the front. Okay, the square root of u becomes u to the negative 1/2 power, which we can anti-derive by adding 1 and dividing by 1/2, which means multiplying by 2. So these ones simplify, and this becomes your final answer. Okay, so hopefully you are more familiar with the algebra that happens when we do u substitution and we're taking the antiderivative of something that's kind of complicated. Hopefully this helps.